Hey everyone, welcome back to ML Works. In this video, we'll learn how to run a Cuda program in Google Colab. So in the previous video, we executed a program and which is parallel vector addition in a local machine, and we were able to get the results for the Cuda program. And since many people won't have GPU based system, you can go ahead and use Google Colab and run your Cuda programs. So first what we'll do is we'll first switch to Google Colab environment, and there we'll be switching to a runtime which includes GPU. And once that is done, then we'll check for NVCC version and see NVIDIA SMI, see the details related to the GPUs. And then we'll install and load NVCC for Jupyter, and we'll write our Cuda program, and then we'll compile the Cuda program and view the results. So let's get started. So first thing is, this is my Google Colab environment. So you have to first log in into your Gmail, and then you will be able to go to colab.research.google.com, and there you can create your notebook. And once that is done, you can switch to the runtime. As I said, first we'll be switching to GPU runtime. So you just have to click runtime and then change runtime type and select T4 GPU and save it. So it is already connected. So for you, if you are doing it for the first time, it may take a little time to connect to that environment. And once that is done, we'll be checking NVCC -- version, and we are able to view the version. Then we do NVIDIA SMI. This will give the GPU details. So it is around 16 GB VRAM is present, and what is the driver version that is present, and other details, if it is occupied or not, anything is occupied in the GPU or not. So this is with respect to checking the version of NVCC and NVIDIA version. So the second step would be to install and load NVCC for Jupyter. So pip install NVCC for Jupyter, and then once this is installed, you want to load extension and give NVCC for Jupyter. So this is required for running your Cuda programs in Jupyter Notebook. So we are doing this 2 steps, and it is already installed, and we are able to load the NVCC for Jupyter. Next is we have to copy paste the program. So in previous video, we wrote a program for vector addition in parallel. So I'll just copy this piece of code, and before we run it, I just had to add here Cuda. So this is the magic command that is required for running Cuda program. Or even before doing that, right, what I'll do is, instead of this, I'll do write file, and this file name will be vector addition.cu. This is the name of my file name, and then I'll copy the file or the code. So just to give a brief about this code, what we do is, first we import the package that is for performing IO, and then there is for math operation we import cmath. And here we create a function which is a kernel function which will be executed in the GPU. So whenever a function call is made to vector add, what will happen is the GPU will run multiple threads, and then it will run this particular function in those multiple threads in parallel. So the major thing is to remember is this global qualifier, because this will ensure that your standard C or C++ function is turned into a kernel function which will be executed in GPU. So this is where we perform the operation in parallel, and each of those value or element in the array will be stored in a thread, and the action will be performed, the operation will be performed. So if there are 10 elements, there will be 10 threads, and those 10 threads will run in parallel and calculate your final result, which is the vector addition. So this is kernel function, and then we have our main function here, which is standard C++ function. Here we initialize our variables for arrays and the number of elements present inside an array. And here we update our array, which is A and B, with some values. Then we declare certain pointer variables which will be pointing to the address inside the GPU, and we assign the memory here for the GPU, and we map the variable name and what is the size of each variable. And then we move the data from our which is in CPU, which is present in CPU. This is A and B are present in CPU, so we move that to Cuda memory, DA and DB variable, and we perform Cuda memory copy host to device. So host represents CPU, device represents GPU. So we move our A and B to GPU device, and then we kickstart our kernel function by setting the grid size and block size. Block size represents the number of threads in each block, and grid size represents the number of blocks. So we call the vector add, which is the kernel function vector add, and pass our grid and block size followed by the parameters. And once you do that, the calculation will, vector addition will happen here, and it will be stored in C. Okay, here. And in C it refers to DC, and since we have calculated or operation is completed, what we do is we move back to host device, host memory. So what we do is from device memory, which is in GPU, we move it to our CPU. So that's why it's given here, Cuda memory copy to device to host. So device refers to GPU, host refers to CPU. So then what we do is we just print everything, what is present in array A, what is present in array B, and after the addition what is present in array C. So if you see here, right here somewhere we have allocated 3 variables, okay, some memory inside Cuda device. So we free that specific variable and release those memory and return finally 0. So this is the basic of that program, what we have written. Now what we have to do is we just run this. So what will happen, right, by giving this specific magic command write file and pass the file name, so the whole code, right, this whole Cuda code will be moved to this specific file, vector addition. So let me run this. So writing vector addition.co. Yeah, there will be a file created now. If I go here, you will be able to see this vector addition. So let me open it. So this is the file that got created. Now what we have to do is, if I go back to VS Code, and what is the step? We have to compile the Cuda program and view the results. So first I'll be NVCC, and since this is with respect to the Colab environment, because there will be compatibility issues between NVCC and the GPU. So what we have to do is we have to set arc is equal to SM75, and then we have to run the program, which is vector addition Cuda and -o vector addition. So what will happen is it will use this architecture to run on top of this Cuda code, and the results will be stored inside vector addition. So let me run this. So this is okay. What I'll do is I'll skip this now for now. Let me run this one. Now let us see here, vector addition. Yeah, so in this file, okay, it won't show up because we are running it in, yeah, here you will see, yeah, so this is throwing an error. So what I'll do is I'll go to command to run NVCC in Colab arc value, architecture value. So here it will show us that specific command. Yeah, so this is the way you have to send the command, architecture command. So here you have to do -arc is equal to SM75, and then you have to perform the vector addition. So yeah, so it took vector A and vector B, it performed the calculation or addition between these two and gave us the final result. So this is how you have to compile your Cuda code in Google Colab. Okay, major important thing is this architecture value. It has to be SM_75. So yeah, with this I'll be concluding this video. Thank you for watching.